One, one and all. So yesterday we began the block with an introduction to the forecasting methods. We are through with what do we mean by forecasting, how to conduct, what are the steps through which we can conduct the forecasting, and how to choose the methods, several quantitative and qualitative methods we have discussed an overview. So, going in detail along with one of the methods, or you may say one of the techniques, that is your correlation, which speaks about, or you may say, which is the you may say tool, or which is the method measuring the strength and direction of a linear relationship between the two variables. This speaks about how the two variables are associated with each other, whether they are positively associated, negatively associated, linearly associated, multilinearly associated, so on and so on. The correlation speaks about association between two variables. It speaks about, or you may say, it measures the strength of the association and the direction of the association. The direction, by direction I mean whether it is a positive direction or whether it is a negative direction of a linear relationship between two variables. Going forward, basically in this particular session we will be learning what exactly the correlation means, what are several types of the correlation, how can we compute several coefficients of correlation, and how can we interpret the result of the coefficient meaningfully, and how can we use it for testing the significance, and what do we mean by the rank correlation, and what is that, what are the practical examples, or how can we practically use this correlation. These are the topics of the discussion today. So, moving forward, to start with, we should know about what exactly correlation means and why should the managers learn correlation, or why should the managers care about this correlation. By correlation, we mean it is a statistical measures which expresses the extent to which two variables change together. It captures both direction, positive or negative, and the strength of a linear association, but never proves cause and effect. Okay, the correlation is basically a statistical measure which expresses or which measures the extent to which the two variables change together. That means whether the temperature changes, what will be the, or if the temperature changes, what will be the effect of a certain drug on a human being or for a specific disease. So whether with the temperature change, the drug effect will change effectively. That means it will be acting fast or acting slow, those things. And it captures both direction. That means whether it is positively moving, that means if one is increasing, the other is also increasing, that means both are positively directed. And if one is going forward and another is coming forward, coming backward, then it is negatively related. So why managers care for the correlation? Forecasting demand from price, income, or seasonality signals, we require to measure the correlation between the variables like price and income, and the seasonality, the change in weather, the change in the timing, and so on and so forth. The portfolio construction, that means diversifying across weakly correlated assets. And suppose say you are measuring your HR analytics, linking training hours with productivity gains. So how those that means the number of training hours, whether it is increases, then whether the productivity of the employee is increasing, and so on and so forth. And the marketing relating and spend with sales lift or brand recall. And now in case of operations area of the managers, diagnosing the defects against a certain machine speed or speed shift length, or diagnosing the number of defects amongst a lot, and so on and so forth. So going forward, we may say types of the correlation. If we say types by direction, then they are positive, negative, and zero. That means if the both the variables move in the direction, then the correlation is called as your positive correlation between both the variables. That means suppose say the income of an employee increases, then the savings also increases. So income and savings of an employee or of a personality are positively correlated. By negative, we mean the variables move in opposite direction. If the price of a, suppose say the vegetables in the market, the price is fluctuating today, suppose say your tomatoes are per kilo it is 30 rupees, then you may purchase a kilo. And if suppose say during the peak summer, the price of the tomatoes will increases, that is suppose say 60, 80, in that case you will be purchasing less. Or that means if the price goes, then the quantity demanded will be decreasing. In that case, the price and quantity demanded are negatively correlated. And zero, that means no systematic linear movement between the variables. Suppose say two variables, they don't change or they don't depend on each other. In that case, you may say they are not correlated with each other. Okay, that means the choice of the clothes of two human beings, that doesn't match, there is no correlation in that case. In by number of variables, the correlation can be categorized into simple correlation, partial correlation, and multiple correlation. By simple correlation, we mean the relationship between two variables only. Okay, in case of partial, the relationship between two while others are held constant. And in case of multiple, one variable studied against two or more jointly. And by form, that means that it is linear, non-linear, and spurious. The spurious, or we say it as nonsense. The linear, constant rate of change. Points cluster along a straight line. Okay. Non-linear rate of change varies. Curvilinear pattern. Suppose U, S, exponential, and so on. Spurious means statistical link without any real underlying relationship. Okay. Going a bit detailed, positive, both variables rise or fall together. Study hours and exam scores. The study hours taking in X and exam scores in Y, it goes in a positive direction. That means both will be moving, rising or falling in the same direction together. Negative, one rise as other falls. That is price, and if the price increases, quantity demanded decreases. Zero or no constant pattern of movement. The shoe size and intelligent quotient of a personality. These two variables are not related with each other, so there is no consistent pattern of movement in amongst these two variables if we will be taking it together. So the graph is very erratic, that doesn't speak anything either positive or negative. Similarly, by linearity, we say the constant rate of change, points cluster along a straight line. By curvilinear, the pattern bends, maybe U-shaped, maybe S-shaped, maybe exponential. And non-linear, any non-straight relationship, your Carl Pearson's R will understate the link. So, this is the worked examples. Suppose a positive and linear advertising spend and sales lift. That means the amount that a company spends towards the advertisement and the sales performance in the market, a clean upward straight line. So these two are positive and they are linear. Negative and linear interest rate and loan demanded. If the bank's in loan interest rate increases, then the people will not go many for loan. So in that case, the demand for the loan decreases. So interest rate, as interest rate increases, the loan demand decreases. So it is a steady downward straight line. The curvilinear supposes stress and performance. The depends, it rises, peaks, then falls, inverted U. Curvilinear. So the correlation coefficient, a single number, it is a single number denoted as small r that summarizes both the direction and the strength of a linear relationship. Okay, your coefficient of correlation speaks about the direction and the strength of the linear relationship. It is a coefficient, is a single number which presents or which speaks about the relationship direction and strength between the two variables, and that it is being denoted as small r. If the absolute value of the r is equal to 1, if it comes out to be 1, then you may say that the relationship between the two variables is perfect and linear. The points lie exactly on a straight line. Okay. If the absolute value is between 0.75 and 1, then the association is strong, the trend is clear and reliable. And suppose say your coefficient turns out in the value between 0.5 and 0.75, then the association between the two variables for which you have computed the coefficient is moderate association and pattern is visible, but not, the strength is not that clear, it is a bit noisy. If the value of R is between 0.25 and 0.50, then the association is very weak, the trend is very faint, bleak trend. Okay, and if the absolute value of the coefficient of correlation is less than 0.25, then the association between the variables is very negligible, linear association. It is treated as mostly or essentially uncorrelated. The the variables for which the coefficient of correlation is less than 0.25. You may say both the variables, the association between them is not that significant and they are mostly uncorrelated. The sign of R, we have interpreted all these points with absolute value of R. That means your R may be a negative value or may be a positive value. So your R gives, that sign of the R gives the direction. A high absolute R never on its own implies causation, cause and effect relationship. Okay, so no linear perfect negative a -1 and perfect positive if it is +1, and if the value is plus 0.5, then moderate association in the positive direction. If it is minus 0.5, then it is moderate association in the negative direction. And if it is -1, then perfect negative relationship and perfect relationship in the negative and perfect relationship in the positive, and so on. So the correlation coefficient, the formula is summation. It is also called as your Pearson's product movement coefficient. The formula is that xi minus x bar into yi minus y bar, summation of this divided by square root of summation xi minus x bar whole square into summation yi minus y bar whole square, where xi is the value of one variable and yi is the value of the other variable, values of the other variables, random variable both are, and x bar is the mean of one variable, that is x, and y is another variable, that is y. Okay, so it is bounded by minus 1 and plus 1, a pure number with no units. Your correlation coefficient, as because it is a ratio, it doesn't have any unit. It is symmetric in x and y. That means whether you calculate whether you say the correlation between xy or yx, both are same, are xy and ryx. Invariant under linear rescaling, change of unit or origin. If you are changing the unit or you are changing the origin, then the scaling, it is invariant. And equivalent form or covariance of xy by standard deviation of x into standard deviation of y. Okay, this formula can also be written as the correlation coefficient is equal to covariance between x, y, and standard divided by standard deviation of x and standard deviation of y. Okay, and r square is the share of variance in y explained by a linear fit on x. Okay, the assumptions that have taken while calculating your correlation coefficient is that assumptions and cautions are: it captures only linear part of an association. The curves and U-shapes can read as the correlation between the variables as approximately zero. Okay, the sensitive to outliers, that means if on any extraordinary condition your value of the variables are either going very high or are, you may say, behaving in an indifferent fashion than the other variables, that is called as your outliers. So it is sensitive to outliers. A single extreme point can inflate or hide your r. Okay, it is very sensitive. So in that case, the association between the variables calculation will not be proper. So both variables should be continuous and roughly bivariate normal for inference on R. And for ranks of or monotone but nonlinear data prefers Spearman's rho. This symbol is called as your rho, or Kendall's tau. These two are the rank correlation coefficients, and we will be discussing in the later slides. So correlation is not equal to causation. Lurking variables and spurious patterns are common. So interpretation, so that you may make with your correlation coefficient. Suppose say your R is plus 0.82, then it's a strong positive trend. R square is equal to 0.67 in that case, and about 67% of variance is shared. Similarly, if R is equal to minus 0.30, then your weak negative drift pattern is real but easily masked by knowledge, as because the value is very weak, 0.30. If R is 0.05, in that case, we said in the previous slide also that effectively no linear ring. It don't fit a straight line for prediction. So if R is equal to minus 0.97, as we said, if it is R is equal to minus 1, then it is perfect negative correlation between the variables. So as because it is nearing perfect, so near perfect inverse relationship, one variable almost determines the other. The one of the types, you may say, your Karl Pearson's coefficient of correlation. The formula is R is equal to summation x minus x bar into y minus y bar divided by square root of summation x minus x bar whole square into y minus y bar whole square, where x bar and y bar are arithmetic means of the two series x and y respectively. Okay, and key properties of your correlation coefficient of correlation is it is bounded between, as all correlation coefficients are between -1 and +1, independent of units of measurement as because it is ratio, and independent of change of origin and scale, whether you will be changing the origin or the scale or the series, then the value of R never changes. Just, or you may say it remains constant. The symmetric, it is whether you say Rxy equals to Ryx. And geometric mean of two regression coefficients, and it is sensitive to extreme values, that is outliers. Okay, and this, the 0 is non-linear association, and +1 is perfect positive and -1 is perfect negative. Spearman's rank correlation, when to use it? If data are qualitative and can only be ranked, suppose say your exam results, they are in grades, so the students can be ranked as grade 1, 2, rank 1, rank 2 and so on. In such situations, you can calculate the rank correlations. Data are qualitative and can only be ranked. In that case, Spearman's rank correlation can be used. The distribution is known or far from normal, and the relationship is monotonic but not essentially necessarily linear. Outliers exist, ranks so often their effect on the coefficient. Okay, so your formula will be rho is equal to 1 minus 6 into d sum of d square divided by nq minus n, or else you can write it as n into n square minus 1, where d is the difference between the paired ranks and n is the number of paired observations and rho is the rank correlation coefficient, and the value of rho as it is bounded between -1 and +1. And for tied ranks, add a correction factor, that is m into m square minus 1 by 12 for every set of m tied observations. Okay, that means two people can be having the same rank. Okay, suppose say one example of Pearson's correlation coefficient calculation. 5 firms A, B, C, D, E, they spend X rupees and lakhs towards their advertisement, and Y is the sales figures in lakhs. So mean of your advertisement spending is 6 and this sales is 21.2. So cross product x minus x bar and y minus y bar in each case, and taking the sum together is 88. Okay, you can take it, calculate that. This step by step. Okay, center the data by subtracting x bar minus 6. X bar is equal to 6, from which x and y bar is equal to 21.2 for each y. Okay, so you say 2 minus x bar, 2 minus 6, 4 minus 6, 6 minus 6, 8 minus 6, 10 minus 6, and the square of it, each one together will be 40, and over here it is similarly 12 minus 21.2, 18 minus 25.2, 20 minus 21.2 and so on, and sum of cross products, that is your x minus x bar and y minus y bar taking all together is equal to 88. Sum of the square deviations, sum of this is equal to 40. X minus x bar whole square summation is 40. And the other one, that is y minus y bar, is equal to 196.8. Applying the formula, cross product divided by summation x minus x bar whole square into summation y minus y bar whole square, that is equal to 88 divided by 40 into 196.8, and square root of that. That is equal to 88.72, and your R will be equal to plus 0.992. That means there is almost a perfect positive linear association across these five forms. Okay, so the correlation is not a causation. A high R tells you two series move together. It never tells you that one is driving the other. Okay. Coincidence means two unrelated series may trend together by chance, especially over short windows. Whereas common cause, a third variable drives both ice cream sales and drowning. Both rise with summer heat. But reverse direction, the supposed effect may actually be the cause. Fitness and exercise are mutually reinforcing, but one is not causing the other. The next is testing the significance of the correlation coefficient. It is a graduate treatment of the student's t-test for rho, Fisher's jet transformation, assumptions, power, and interpretation. Okay, so why we should test the correlation coefficient? The simple correlation R is a point estimate of the population correlation rho. Okay, even when rho is 0, finite samples produce non-zero R purely by chance. So R on its own cannot tell us whether two variables are linearly related in the underlying population. So a formal hypothesis test H0 is equal to rho is 0 against an alternative, that is rho is not 0. It quantifies how unlikely the observed are under the null hypothesis, separating real linear association from sampling knowledge. Okay, this next slide really lays out the four pieces. That is, number one, inference target, that means treat rho as the unknown parameter and R as a noisy estimator. Frame the null as rho is equal to 0 and read p-value or confidence interval of the sampling distribution. The second one is exact small sample test, that is t-test, and it is a student's t with n minus 2 degrees of freedom, exact under bivariate normality, and the workhorse for small samples. The third one is general rho 0 not equal to 0, is Fisher's jet, which is approximately normal with variance 1 upon n minus 3, enabling your tests of rho is equal to rho 0 and confidence intervals back transformed into R. The diagnostics is check bivariate normality, linearity, and outliers. Report effect size R square alongside p values, weigh power, and avoid confusing significance with practical importance. Okay, recapping, you may say this is our Carl Pearson's correlation coefficient. The equivalent of this for your sample is sample xy, sx, sy, whereas xy is the sample covariance. Similar is the case, the properties under your R is bounded by -1 and +1, unchanged under affine transforms of x and y, measures linear association only, non-linear dependence may yield R equivalent to 0. Estimate of rho is equal to covariance of xy divided by sigma x into sigma y, the population parameters. It is biased in infinite samples. Bias is equal to minus rho into 1 minus r rho square divided by 2 into n minus 1. That gives us the sampling distribution of R under null hypothesis. Rho is equal to 0. Under the bivariate normal model with rho is equal to 0, the sample size, the density of R is the gamma n minus 1 by 2. It is a gamma distribution with this density function. It is symmetric about 0 with expectation of R is equal to 0 and variance of R is equal to 1 by n minus 1. Okay. Under the bivariate normal model with rho is equal to 0 and the sample size n, the density of R, or you may say the PDF of R, is a gamma distribution. The key consequences of this is that it is symmetric about 0 with expectation R is equal to 0 and variance of R is equal to 1 upon n minus 1. It is a heavy tail for small n and converges to normal limits as n tends to infinity. Okay, so for finite n, the exact test uses a monotone transformation of R that follows the student t distribution, which is derived next. Okay, formal hypothesis are like this. These things we have discussed in our previous sessions. This is two-sided null hypothesis, right-tailed hypothesis and left-tailed hypothesis. Okay. Rho is equal to H0, rho is equal to 0, H1, rho not equal to 0, it is two-sided hypothesis. And rho positive and rho negative. Detects any linear association, it is pre-specified positive direction and this is left-tailed pre-specified negative direction. Okay, choose the alternative before viewing the data, specifying direction, post hoc, inflates, type 1 error. Okay, the test statistics is students T with n minus 2 degrees of freedom and the formula for which T is equal to R square root of n minus 2 divided by square root of 1 minus R square. And this is student T with n minus 2 degrees of freedom under null hypothesis rho is equal to 0. The regress y on x, the slope of beta satisfies beta cap is equal to r dot sy by sx under rho is equal to 0. S, so beta is equal to 0 and the ratio beta cap divided by standard error of beta cap follows students T with n minus 2 degrees of freedom. So algebraic simplification gives the formula above. The correlation test is exactly the t-test on the regression slope. Okay. So assumptions for the exact t-test is that number 1, the sampling is random sampling. The pairs xi, yi are independent and identically distributed. They are bivariate normality. The joint distribution of x, y is a bivariate normal distribution. And the linear relationship, any association between x and y is linear in form. Homoscedasticity, that is variance of y given x, is constant across x implied by the 2. And no influential outliers, that is Pearson R, is sensitive to leverage and outliers. If bivariate normality is doubtful, we should use a permutation test or the Spearman rank correlation as a robust alternative. Okay, if your distribution is not bivariate normal, if you have got any doubt that the distribution is not bivariate normal, joint distribution is not coming out to be the bivariate normal, in that case we may use Spearman's rank correlation as a robust alternative. Okay. So decision rules in case of critical value approach, if two-sided test, reject H0, reject the null hypothesis. if the absolute value of the t calculated is greater than the tabulated value at alpha by 2 and minus 2 degrees of freedom, and so on. Similarly, p-value approach, if your p-value is equal to 2 into p of this, then accordingly we have to report the exact p, the confidence interval for p rho, and r itself, not just the binary decision. The Fisher's Z transformation test, the student t-test only applies under null hypothesis rho is equal to 0. For general null hypothesis rho is equal to rho 0, use Fisher's variance stabilizing transform. And the Fisher's Z distribution Z, the value goes like this: half of log E to the base E, 1 plus R by 1 minus R. And tau 0 is equal to half log E, 1 plus rho 0 by 1 minus rho 0, and so on. So confidence interval for rho is from a walled interval on this Z scale, it is Z plus minus Z value at alpha by 2 into root n minus 3, and back transform each endpoint like this. And the interval is symmetric in R, appropriate because the sampling distribution of R is skewed when rho is very large. Absolute value of rho is very large. So, suppose taking into consideration certain calculations, study hours versus exam scores. Suppose a researcher records X is equal to weekly study hours and Y is equal to final exam score for N is equal to 10 graduate students. The test whether the variables are linearly associated at alpha is equal to 0.005. That means at 5% level of significance. So your X is weekly study hours, Y is the final exam scores, and the number of students for which these things are taken is 10. So if you will be calculating X bar, mean of X, that is coming out to be 13.0, and mean of Y is 72.0, and summation Xi minus X bar whole square, it will be this much, and summation Yi minus Y bar square is equal to this much, and summation cross product is equal to sum of that is 612.0. The hypothesis is 0 is rho 0, and H1 is rho not 0, it is two-sided at the level of significance 0.05. This is step 1. We have calculated summary statistics. Okay, we have calculated mean, we have both the series, we have calculated the square of the deviations for both the series and cross product. So next is your sample correlation. R is equal to this much, taking together the values 0.9961. So R square is equal to 0.9921, is approximately 99.2% of variance in Y is explained linearly by X. So your test statistics is equal to 31.69 with degrees of freedom as 10 minus 2 is 8. Okay, then the critical value versus observed critical value at, it is a two-tailed at 5% level of significance. So we will be taking the t value, critical value as 0.025 with 8 degrees of freedom. It is 2.306, and observed value is also 2.306. So p value is coming out to be 31 0.69 is less than 10 minus 9. So the decision is that the reject your H0 at alpha is equal to 0.05, that is 5% level of sigma. Okay. So pitfalls, effect size, and the power of this particular calculation, this particular test is that with large n, even r is equal to 0.05 is significant. Always report r and the class interval alongside p. The caution, the significant rho not equal to 0 implies linear association, not causal direction. Okay. The outliers in leverage, a single influential pair can flip the sign or magnitude of R. Always your R is influenced by outliers. Any, you may say, non-normal observation. The sample size for power, the detect rho is equal to 0.30 with 80% power at alpha is equal to 0.05. N is equal to 85 is required. Okay, so your sample size should be more for power. And range restriction, truncating X or Y attenuates R towards 0. Truncating X or Y. That means if the range is restricted, then your R will be moving towards 0. That means the association between the variables will be 0 if the number of values is less. The multiple testing, when screening many correlations, control your FDR or family-wise error. So key takeaways from this so far is test rho not R, as because R is a sample point estimate and significance testing concerns the population parameter rho. Use T with n minus 2 degrees of freedom, as T is equal to R square root n by 2, n minus 2 divided by square root of 1 minus R square is exact under bivariate normality for rho H0 is rho is equal to 0. And Fisher's jet, general rho 0 and class intervals, use this for rho is equal to rho 0 but and to build asymmetric confidence intervals. Check assumptions, that the assumptions should be that the linearity and both the variables will be having bivariate normality. This should be independent, and in that case, if not bivariate, then use Spearman or permutation when violated. So, extension, you may say rank correlation, that is Spearman's rows and Kendall's tau. Why ranks? The distribution free, that means if your observations or if your variables are not following any distribution, then we can assign them with certain ranks. If your variables are not quantitative, in those situations, your ranks should be there. So distribution free, robust to outliers, and non-linear monotone relationship, no normality assumptions on X and Y, as because they are not quantitative. So Spearman's rows is Pearson calculation, a Pearson correlation applied to ranks, that is your Spearman's rows. And this is equal to 1 minus 6 summation di square and n into n square minus 1 with no ties. If there will be any tie, then we have to add a smoothing factor to it. The Kendall's tau, it is equal to tau is equal to C minus D divided by n into n minus 1 by 2, where C and D count concordant and discordant pairs across all n, choose 2 pairs. So we will be discussing this in the coming slides. So significance test under null hypothesis, independence, use the exact permutation distribution for small n, normal approximation for large n. If you are considering rank correlation. When to choose which? Spearman for general monotone trends and Kendall for small n or many ties, either for ordinal data. So distribution free alternative of your Carl Pearson's correlation coefficient, sensitive to monotone and not strictly linear dependence. This is your rank correlation. So Spearman's rank correlation, the formula is 1 minus 6 summation d square divided by n into n square minus 1, where di is equal to rxy minus ryy are rank differences. Equivalently, Pearsons are computed on the ranks of x and y. With ties, assign mid ranks. That means if suppose say two people are having 3 and 3, in that case take the mid ranks, that is 2.5 and 2.5. Okay, and apply the similar formula directly. So range, as usual, it is bounded by -1 and +1 for any strictly monotone x and y. So monotone invariant unchanged under any strictly monotone transformation of x and y. It captures monotone, not strictly linear association, robust to outliers and skewed marginals, significance for small n, and for n more than 10, it is approximately T with n minus 2 degrees of freedom under null hypothesis. So Kendall's tau, it is C minus D by n into n minus 1 by 2, C and D, number of concordant and discordant I and J. With ties, your tau A is C minus D divided by n0 minus n1 into n0 minus n2, where n0 is equal to n into n minus 1 by 2. Where n1 and n2 are correct for ties, we will be making a calculation for this for your better understanding. So your range, as usual, any correlation, the probability interpretation, tau is equal to probability of concordance minus discordance, probability of discordance for random pair of observations. It is monotone and invariant, large sample significance, and versus Spearman's, it is typically tau has a cleaner sampling distribution and handles small n or many ties more reliable. So Kendall's tau calculation, suppose say we are having ranks of 5 students on 2 tests, X rank and Y rank. Total pair is n into n minus 1 by 2, that is equal to 10. Concordance, both ranks move the same way, that is A C, A D, A E, B C, B D, B E, C E, D E. That is concordance. If the ranks move the same way, then they are concordance. So your C is equal to 8. Discordance, ranks move in the opposite, A, B, that is, and C, D. Sorry, C, C, D. Okay, that is discordance are 2. So with ties, suppose say over here we are having 3, 4, and over here we are having 4, 3. Both the ranks are moving in the, they are in the tie position. In that case, we will be using 3.5 and 3.5. 4 and 3, 4 plus 3 by 2, that is 3.5 and 3.5. So the tied pair CD is neither concordant or discordant. So count C is equal to 8, concordance, D is 1, discordant, and the AB pair, 1 tied pair. So tie correlation, corrections, N0 is equal to 10, N1 is equal to 0, N0 is equal to 10, N1 is equal to 0, no X ties, N2 is equal to 1. Okay. So your tau is equal to this by using our formula. C minus D by 10, 8 minus 2 by 10 is 0.60. And tau B is 7 with ties. It is 7 square root of 90. Yes. With the same data, all the 3 coefficients we have calculated, and they are coming out to be like this. What if one score is an outlier? Your Pearson R jumps one. Suppose the last score is 200. Taking one data, same data, we have calculated all the three coefficients, and if one score, suppose say the last score goes to 200, then there will be this variation. So your Kendall tau is and rho, that is Spearman's rank correlation, both are more robust than your Pearson's R. Interpreting tau value, if approximately it is between 0 and zero point 0.1, then negligible, that is essentially no monotone link between your concordance and discordance. If 0.2, then it is a bit weak, a random concordant pair bits, discordant by 20%. And 0.5 moderate, if it is 0.8, very strong, and 1 perfect. Ranks are identical or perfectly reversed, no discordant pairs. So rule of thumb over here is that the tau values run smaller than your Spearman's rank correlations. Do not compare cutoffs across metrics. So this is one more calculation for your Spearman's rho and Kendall's tau with the same data, and the values, just we wanted to show the how the value varies. And comparing Pearson's R, Spearman's rank correlation, and Kendall's rank correlation. You may say your Pearson's, it is optimal when X and Y are is bivariate normal, highest power in linear trends, and sensitive to outliers and non-linearity. Whereas these two, they are distribution free, detects any monotone trend, robust to outliers. It is not varied that much. If there are outliers, and skewed marginals loses some power if data are truly linear and normal. And Kendall's tau, it is interpretable as P concord and probability of concord and probability of discord, best for small n or many ties, lower magnitude than your Spearman's rho, but cleaner sampling distribution. Okay, the power comparison, taking your rho values, this is one more, it is illustrative that powers at point, or you may say 5% level of significance, and n is equal to 30, that is sample size is 30 from your Monte Carlo studies, asymptotic relative efficiency of your Spearman's rho and Kendall's tau versus your Carl Pearson's R under bivariate normality is 9 by pi square, which is approximately equal to 0.912. Okay, the practical applications, why correlation is important. Correlation is basically one of the most widely used statistical tool, which is basically used in economics and business because it helps identify and quantify relationship between variables. The key purpose over here is it measures degree of association between variables, helps understand business phenomena, supports forecasting and decision making, provides the foundation for advanced and analytical techniques. Your correlation indicates association, not causation. That is, strong correlation suggests that variables move together, but it doesn't prove that one variable causes other. Okay. That is, if income is increasing, expenditure on premium products is also increasing. However, if ice cream sales increases and drowning incidents increases, may be correlated due to some other, not because one causes the other. Okay? So it is not a cause effect. So correlation in business decision making, it supports managerial decision. Your Managers frequently use correlation analysis to understand relationships that influence organizational performance. Advertising expenditure, sales revenue, customer satisfaction, and customer relation. Similarly, human resources, people, training hours, and employee productivity, employee satisfaction, and organizational performance, finance, risks taken, and the returns received, interest rates, and the investment decision, they all are related. So, key benefits, correlations help managers identify the variables most strongly associated with business outcomes. It is tool for your regression analysis. One of the most important application of correlation is the development of regression models. A construction company wishes to forecast annual sales. Potential influencing variables may be population growth, construction employment, building permits issued, housing demands, income levels, and so on. Calculate the correlation between each variable and cells. Identify variables with high correlation. Include significant variables in the regression model. So your managerial advantage over here is it improves forecasting accuracy, eliminates irrelevant variables, reduces model complexity. It is used in factor analysis, which factor will be influencing where, in to what extent. That is the basis of your factor analysis. Factors may be the variables, product quality, packaging, brand distance, the customer perceived value, and so on. Correlation in forecasting and time series analysis, forecasting future for business. Correlation plays a critical role by taking your time series data. Role of autocorrelation. Autocorrelation measures the relationship between the variables. So detecting the trends. Examples may be monthly sales data often show trend component, seasonal component, random component. Autocorrelation helps. Sure. Your correlation is often the first step in transforming your raw data into managerial knowledge, business intelligence, and strategic action. Your correlation helps managers to understand relationship among variables, select predictors for regression models, conduct factor analysis, improve forecast accuracy. By factor analysis, I mean each and every outcome depends on several factors, and which factor is what influencing how much. That is what it will be the factor analysis. So identifying trends and seasonal patterns support evidence based decision making. So next is autocorrelation, understanding patterns in time series data through lagged relationships and statistical dependencies. Lagged relationships and statistical dependencies. Okay. Autocorrelation measures how a time series relates to a lagged version of itself. It reveals whether the past values carry information about future values, capturing the persistence of trends and rhythms of seasonal cycles. Values range from -1 to +1 at each lag k. Okay, autocorrelation function rho k is equal to covariance of yk t and t ytk by variance of yt. Correlation between a series and its own past k periods back. The formula is at, you may say, lag k. So your rho 1 is high, yesterday strongly predicts today. Classic random back behavior, slow decay across lags, spikes at lag 7, 12 and 24, weekly, monthly and daily seasonality, alternating signs, oscillatory behavior of mean variation, all bars inside plus and minus 1.96 to root 10. Okay, if your range of rho k is between -1 and +1, if it is -1, then strong anti-persistence, and if it is +1, it is strong persistence. Okay. So autocorrelation in the real world where time series memory drives decisions, your retail demand for the autocorrelation function surfaces persistence and seasonality, turning the stream into actionable foresight. So here, use cases, retail demand forecasting like signals, weekly unit sales, promotion calendar, weekly, annual or seasonality sales, etc. Financial and volatility risk and other demands like weather and climate, daily temperature and rainfall cycles, IoT and manufacturing, macroeconomics, unemployment, inflation and policy lags. So key takeaways, you may see correlation captures co-movement. Your Pearson, Sperman and Kendall summarizes direction and strength but never proof causation. Autocorrelation is equal to memory in time, that is the autocorrelation function measures how a series correlates with its own past, revealing persistence and seasonality. The stationary is the foundation, the difference and transform of until ADF and KPSS agree, otherwise forecasts and inference break down and ACF, PSF drive ARIMA. You identify P and Q from your correlogram cutoffs, validate residual with Lagrange function box, and then forecast with confidence. So then in the next session, we will be discussing regression with this sorted agenda, and if correlation tells us two variables move together, regression tells us how much they move together. So that is what comes next. Thank you.